Hi, my name is Leonard Sauvé, and today I will present the results concerning our work on elucidating the automatically detected features used by deep neural networks for RFAM family classification, a work that is being done by Tom McDougall and myself um, from University of Montréal. So in this study, we show that deep feed-forward neural nets are able to accurately classify RNA families directly from RNA sequences. We demonstrate to what degree those models use length, as well as nucleotide and dinucleotide composition, as well as higher order subsequences that are present in the RNA and that allows accurate predictions by the models. And we show that by selectively obfuscating combinations of those features. For our methodology, we used as input data 7,405 RFAM sequences from 24 families of varying length. We then padded those sequences to 9600 using blank nucleotides, zeros, that we call zero padding, or random nucleotides with uniform distribution, which we call random padding. And then in further experiments, sequences are shuffled internally, then padded with zero padding or random padding. We call them NUC shuffle. The final preparation scheme for this experimentation involves shuffling the sequences within a family according to dinucleotide content of that family. We'd call that dinucleotide shuffle, which are then padded with zero padding. Then for the implementation of the models, we one-hot encoded all the sequences so that the input space is now 10,200. We then feed that to a feed-forward neural network with two hidden layers of either 5 nodes or 1,000 nodes in each. We use regularization and we use BCA loss function. The optimization, the optimizer that we use is add-in, and we use mini batches with subsampling. Then for model evaluation, we used a 5-fold cross-validation as an internal validation method. Then we report our accuracy with area under the curve of the receiver operator characteristic. Then we use the RFAM DNN classifier to showcase the convergence after 100 epochs. Onto the results. So we see on the left table 1 showcasing all the accuracy result that we have for our different experimental setups. Then we have on the right the figure that shows convergence of the model for a chosen family. We can see in the middle here that for the zero padding and random padding experiment, that those models have converged to a perfect accuracy for most of the models. Then we see that accuracy will decrease as we introduce more and more randomness in the padding or in the sequence content, meaning that shuffling the sequences as input makes the model less accurate. Now onto the observations that we make. Regarding sequence length, we see that there is no difference between the zero padding and the random padding experiment based on AUC. And we observe two things: that first, they achieve very high performance for this binary classification task. And also that they retain high performance after having the sequence length partially obfuscated by the addition of random padding. Then, for dinucleotide content, by observing the effect of disrupting all sequence information beyond nucleotide composition, the lost performance indicates that higher order subsequences fragment of RNA might be relevant features that the DNN uses to maintain high AUC. We see that from those two columns. So by removing dinucleotide, which is basically saying shuffling the internal sequence of the families, then we lose some accuracy. Then when we add random padding to the rest, noise is sufficiently decreasing accuracy for those models as well. Even if we use a big model, we are not able to achieve better than our original setup. Then for longer interactions, so what we did with the dinuc shuffle experiments is that it forces the automatic feature selection to detect longer subsequences of 3 nucleotides and more that are strong indicators of family identity. So IUC higher than 0.5 for all families shows that these models perform better than random and indicate that DNNs are able to capture the target RFAM blueprint from subsequences, possibly from the presence of or absence of larger than tumors without positional information. We see that from this experiment here, is that as opposed to the original setup, we are not able to achieve good accuracy because the longer interactions are not present in those in the input data. And here I show the references for our work, and we are currently working on improving those findings. And thank you for your time and your attention.